Once again, welcome to this AICT sponsored short term training program on power converters for industrial and renewable application phase 3 under AQI scheme from 14 to 19 December 2020. Now, this is the afternoon session. So, today we have with Mr. Junaid and National Infotech team. And topic of this practical session is implementation of MPPT algorithm of solar PV. And as you know, we are associated with National Infotech Surat from last 5 years. We have organized various training programs for students and faculty members. And of course, we have got a very good output from their side. Again, I request all the participants, please mute your mic when a session will start. Okay, then I would like to welcome National Infotech Surat. I request Junaid, please join the session and start the session. Over to Junaid.
Okay, thank you, sir. Thank you very much, Paresh sir, for kind words.
Yes, sir.
And so I'll start my today's session. We'll start with a little bit of summary of whatever we have done yesterday. So, participants, I would like some input from your side that what are the exercises we have seen yesterday.
So yesterday we have done the fundamental of Weijing block set and STM32 microcontroller, and how to generate the basic PWM signal and the advanced PWM signal that we have seen yesterday.
Yes.
And along with the LCD interfacing.
Yes. Anyone else? Anyone other than Yugal sir like to say something? Okay. So yesterday we seen the few exercises starting with digital output. So we generated some pulse of fixed frequency 1 kilohertz and also 1 second pulses and get it out from the digital output, and then we saw the push button command, the keyboard interfacing, and also displayed it on the LCD. Then we move on to the basic PWM and advanced PWM, how we can use a timer to generate PWM pulses. And we saw that how we can get the complement pulses, and if we want to only use one pulses of the from the complement, how we can do that. That we also seen yesterday. Then we move on to the analog to digital converter. So ADC, we saw the how we can interface with the ADC, and moving on to ADC, we have also seen that how we can the Yugal sir was having some queries regarding how he can change the duty cycle of the uh, pulses. So that we also seen. Then the digital to analog converter, how we can get the signal which is in the microcontroller out from the DAC, and how we can observe it on the DSO screen. That we have seen till yesterday. So today's topic is implementation of MPPT algorithm of solar PV. So let me share my screen. Before I start the topic of the implementation of MPPT algorithm, so if I'll run this small setup video, which the facility available at National Infotech. So this is a so this is a solar panel installed at our facility. So this one panel is of 150 watt, and we will see the data sheet of that too. We will show you in the presentation itself. So these 6 panels we have terminated, so we can connect it accordingly to our need. So right now, as sir explained on the first day, that we are going to use it in 450 watts. So we are connecting these 3 panels in the series. So the power, the voltage of the one panel is VMP is 36 volts. So accordingly, it will be creating around 100 volt in the DC link. So that DC link we are going to use as the input of the boost converter, and after that we are going to boost it up to 250 volt, and with that we will also see the grid connected inverter too. So hope you understand this solar panel connection. So thank you. Okay. So for the demonstration of this part is renewable energy development. Will be using the 450 watt power from the panel. So we are having one panel with 150 watt. So with the the same three panels are connected in series in order to get 450 watt. Okay, and accordingly we will see the our experiment videos, and how we have interface with the how we have developed the code, and with that along with the sensor calibration and everything. So each and every aspects will be covered during this. So starting with the MPPT. So my screen is visible, right? Anyone would like to add something to this, or ask any queries regarding the session, how we are going to see the session? Okay, so we all know that the renewable energy sources, whether it is solar or wind, any of the renewable sources, we want to extract the maximum power possible at any given point, any given time. So, so in order to do that, there are some techniques developed, that MPPT techniques for like perturb and observe and incremental conductance and 3 point tracking and etc. So that so the main aim of this, the we want to operate that, we want to extract this much power available at any given time. Okay, so this is the particular PV and IV curve of the solar. So you can see this is the x-axis is voltage, this I is current, and this is peak power. Okay, so this this is the peak power. So we want to operate it on this point right here. So that is the maximum power point. Okay, so how we can achieve that? So let's say you have this. Let me open the MATLAB. Okay. So here in the MATLAB, this is the one panel we have model. So we give the panel parameters in this, and accordingly it will give us the uh, specific power of that panel. Okay, so the panel which we are using right today is this 150-watt panel. Let me show you the data sheet of it. Okay, so this is the 150-watt panel. So this is the characteristic of that 150-watt panel. So you can see the open circuit voltage is 44.30 volts. Short circuit current is, sorry, okay, short circuit current is 4.51, and you can see the maximum power voltage at maximum power is 36.10. So that suggests that whenever the voltage, one panel voltage reaches the 36.10 voltage, at that time we can get the maximum power. And what will be the current at that point? It will be the 4.16. Okay, so these parameters are for the third of this 150-watt panel. Okay, so this we have simulated in the MATLAB, so we will understand how this we will be seeing this panel works. Okay, so we are as we have seen in the video that we will be using uh, three panels like this. So three panels in series and one parallel connection. Okay. So this is for the standard test condition. So 150-watt, whatever they suggest, they give that 150-watt panel. So it gives 150-watt power at the standard test condition. So standard test condition is 1000 watt per meter square irradiation and 25 degrees Celsius temperature. Okay. So at that time it will give us the maximum power, okay, of 150 watt. So right now here you can see we have set this ISC, short circuit current, as ISC, open circuit voltage or VOC. Then the series and parallel connection we have denoted as a SNP. So this we have again initiated in this callback initial function, and you can see the VOC is what we have seen in the data sheet, the 44.30, 4.50, and 3 series and 1 parallel connection. Okay, so that this will be giving us the 450-watt power. Okay, so here is VPV. So as you know that in the solar connection, let's say this is your solar panel and you attach some variable resistor here. Okay, so you vary this resistance and you measure the voltage here. Okay, and the current here. Okay, so and this is a PV curve. Okay, so we will vary the resistance according and we will vary this resistance, and accordingly our voltage of this panel will be changing. Okay, and the current you can see this current current will be maximum at the short circuit, and when your resistance is zero, your current will be maximum. And you, when and you you vary this resistance, this current will decrease. Okay, and at this point you will get the maximum voltage. Okay, and this is you can see this point. At this point you will get the maximum voltage, which is not maximum voltage, it is the you will get the power of the maximum. And whatever the voltage is there at this point will be denoted as your VMP, which is the maximum power point voltage. Okay, so what is being given in this data sheet? Okay, this VMP, so which is less than this VOC. So in this graph it is 0, and this is VOC, and this point right here, this is your VMP. Okay, and the current you see is this is your IMP current. So is it clear? Yugal sir, is it clear?
Yes, sir.
Okay, thank you, Yugal sir. So moving further, so we know that in this case we will have to continuously changing our resistance in order to get the maximum power. Okay, so what we can do is what we will do is we will uh, design some boost converter for the uh, for the purpose of serving as a maximum power point tracking. Okay, so that maximum so that boost converter will be varying the duty cycle of this our duty cycle of the pulses, and accordingly the voltage will or at the our output will be varying, and it will get the maximum power. Okay, so let me draw it properly. This is the panel. This here it will be the our capacitor, and this will be the inductor. Okay, let me show you in the simulation itself. Okay, so before we go there, let us just see this simulation, how we have simulated this panel. Okay, so in this panel, this we are applying this voltage. We are giving it this voltage, PV voltage. Okay, the panel voltage, and we are varying in the range of 0 to see, this is the 0 to VOC in the range we are operating. Okay, this is 0 and this is VOC. So in between there is this point, which is maximum power, maximum voltage point, maximum power point, which is at that point whatever the voltage is, which is said as a VMP. Okay, so we will be giving the voltage in the range of 0 to whatever the VOC is. Okay, so VOC right now in this case is VOC is 44.30. So we will apply in the range of 0 to 44.30. So at that point, and we know that we are connecting 3 in series, so we will have to multiply this. So the voltage will be multiplied into 3. So we will get 44.3 into 3. Okay, so we will get this 132.9 volt. 132.9, we have to give the now VOC becomes 0 to 132.9. So we will vary the VPV in the range of 0 to 132. So at that point we will get this point, and our maximum power will be what much power? How much power will be getting? Anyone? So we'll be getting 450 watt power, as one panel is of 150 watts. So into 3 we will get 450 watt power out of this. Okay, so this is the current IPV we are getting, and this is the VPV. So we will multiply IPV by VPV and we will get the maximum the power of the one VPV PPV. Okay, so here just we are just ramping it up this VOC into S. So whatever the open circuit voltage of one panel will be giving here, and the series connection, how many series panels we have connected here, which will be multiplied, and it will take 0.1 second to reach whatever the value is here. Okay, so let me clear this. What is this ramping does is, okay, so what this rate limiter does is, rate limiter, let's say you are giving some command, and your command is 0 at initially. Okay, and you want to change it some finite time, you change it to the state it to 1. Okay, so it instantly changes from 0 to 1. So rather than that, what we are doing is, uh, that when we apply the change, so it will take some finite time from here to between here, let's say this, to reach the final value. Okay, is it clear?
Yes, sir.
Okay, so this is how that ramping works, that rate limiter works, and accordingly, and the same way, what we have given the falling slew rate, which will be when your state changes from 1 to 0, or whatever the value is, and then to it becomes lesser. Okay, so that we are seeing here. So let me run the simulation. Yes. So this first signal is what? VPV. Okay, and this is your IPV. Okay, and this is your PPV. Okay, so let us see the waveforms. Okay. So you see this third waveform, so, represents the power of the our PV panels, three series PV panels. Okay, so you see that the power is 450 watt. It is coming 450 watt. Here you can see this is 450, and this is 450 maximum power. It is coming. Okay, and we can also change it to simulate for the one panel. How we can do that is, we will just simply write here this, instead of 3 we will write 1. Okay, and we will simulate it. Okay, so what will be the power now? Before I open, I want someone of you to say that what will be the power right now.
150 watt.
Exactly, 150 watt. Okay, so 150 watt power we are getting. Okay, so this is how this simulate this PV panel is modeled. Okay,
Sir, we will get the same result as we are having the PV array block.
uh, can you specify more?
So we are having PV block in the Simulink, na? So we will
Yeah,
get the similar kind of result with this.
yeah. Actually, it is we are using here is a 2000 MATLAB 2014A. See,
Okay.
so in this 2014 model, there is no PV panels available. That's why we have a model
Okay.
test panel.
Okay.
So other than that, on the whatever the PV panels available on the MATLAB, you are giving the parameters. It is also giving the proper result. You just need this much parameter. Let me show you what are the parameters you need. This VOC it is asking, ISC it is asking, then uh, VMP, VIMP it is asking also. Then these two parameters, temperature coefficient of current and temperature coefficient of voltage. These two parameters it is asking. Just these parameters you put in there, and it will give you the proper this type of curves. This will be same as this.
Okay.
Whatever the panel you using. Okay, we have seen in the
Okay, sir.
latest versions. Okay, just few parameters you have to put, and it will give you the proper results. Okay. So moving on to the our topic was to track this maximum power point. Okay. So how we can achieve that? So we will be seeing there are few methods of perturb and observe incremental conduction and many more step application, many more algorithms. And so we will be seeing this perturb and observe method. So how we can see how we will be achieving getting to this point. So it is also said it is also called this hill climbing technique. Okay, we will see. We will take the samples. Let's see first understand this algorithm itself. So we will sense the voltage and current of the PV. Okay, then we will calculate the power from it. Okay, so then power is calculated, and the difference of the power is calculated, the delta p. Okay, the the power at the latest instant and the power at the previous instance, that we are getting. And if that condition satisfies, then it will be then it will end the process. Okay, if it is not satisfied, it will again check the power. If it is greater than, if the delta power is greater than 0 or less than 0. If it's greater than 0, the delta p is greater than 0, it will go to check the voltage. Let's say this power is more if it is it will check if power, if I can get to this power or not. Okay, by checking the uh, power at the latest instant and the previous instant. Okay, is it getting clear, you will sir?
Yes, sir. Very much clear.
Okay, so we are trying to get here. Okay, at this point, we want to be at this point. So we will check that if it is power, we'll see that if I can go up here or not. So in order to do that, what will it will do that that it will be checking continuously if the power is available here or not. If the power is available here, then it will check the voltage, if I can go to this voltage or not. Okay, if the voltage is also available, voltage is, we can say I can go up to here, then it will go, voltage will also increase. Okay, in order, but right now what are we understanding is, we are just understanding in the in the point of view of voltage. Okay, so it will increase the voltage. Okay, and how, and up till when it will be increasing the voltage, until it gets the power here. Okay, so after this instance, what happens is the voltage is also available more, but the power, the delta p is not greater than 0. Okay, so that's why what it does is, it says you have to decrease the voltage now. Okay, so you will see here, power is not greater than 0. Okay, and voltage is also not greater, voltage is greater than 0. Okay, voltage is also available, we can go to up to the VOC. So it is saying we can also go to this VOC, but at that time what it will suggest, that you have to decrease the voltage in order to get to this point. Is it clear, Yugal sir?
No, sir.
Okay. So up till this point, is it clear that we are trying to get here?
Yes, sir.
So the power we will continuously test checking that if I can go up to this point or not. Okay. Keep your mic on if it is possible.
Yes, sir.
Okay, so we are trying to get to this point. Okay, so in order to do that, what we are doing is we are checking power also, and if power is available more, then it will do that you have to change the voltage, you have to increase the voltage. Okay, if the delta p is greater than 0, yes, okay, it will check the delta v is 0 greater than 0. Okay, if it is delta v is greater than 0, means the difference between the previous voltage and latest voltage sample, and then it will say that you have to increase the voltage. Okay, in order to get to this point. Is it clear now?
Yes, sir.
Okay, and as soon as you reach this point, so your voltage is against, if it is not let's say you have increased the voltage, but as soon as your voltage difference becomes greater than 0, if it less than 0, then it will again say that you have to decrease the voltage. You have crossed the maximum voltage point. Is it clear?
Yes, sir.
Okay. The same way you will get after this point of the after crossing this point, you will check that power is not available more, so it will check the voltage. So the voltage difference will be greater. You see here the voltage difference will be greater. The voltage difference means voltage difference, what delta wave, what it is suggesting is that voltage is this point and voltage is this previous point, so the difference will be greater than 0. Okay, so that when the difference is greater than 0, it will you have to decrease the voltage. Okay,
Yes, sir.
so, and if it is not the case, then it will say that you increase the voltage.
Yes, sir.
Okay, so the same way we will be implementing it in the boost converter. In the boost converter, we are not giving the voltage reference. Instead, we are giving it the duty cycle. Okay, the same is here. Voltage is getting sense, current is getting sense, the power is calculated, delta p and delta v is calculated, the comparison is same, the delta p is greater than 0 or not, delta v is 0 greater than 0 less than 0, and accordingly the duty cycle will just be changing. Okay,
Yes, sir.
so this we will be trying to see in the simulation. Okay, let us see the simulation. Okay, so you can see this is our boost converter. So this is a inductor. So first we will see this is our panel. Okay, and you can see this is 3 series connection. Okay, so 450 watt power we will be getting from these two, and this
Sir, I have one question. How we can decide the input capacitance of the boost converter?
uh, okay, let me show you. Actually, boost converter, in the boost converter, there's a data sheet given by the Texas Instrument. Have you referred it?
For the boost converter design,
Yes, yes.
sir, actually I have referred that one.
Yes.
So the value of input inductance and the output capacitance is okay, but I'm not able to calculate the input capacitance.
Yeah, yeah.
That is why I'm getting the wrong result at the output side.
Yeah, but here we have kept it as a nominal value. This is just 3 microfarad capacitor we have kept. Okay.
Okay.
Okay. It is just to minimize the ripples here. Okay.
Yes, sir. Minimize the ripple of the PV panel.
Yes, yes. Okay. So if you want also that I can provide you the data sheet too.
Okay. So in the data sheet of PV panel, it is given, or in the data sheet of the boost converter,
No,
it is given.
no. Yeah, the data sheet of boost converter I will provide you that how
Okay.
you can design the boost converter so that you can
Okay.
get the whatever the how to select this uh, capacitor, this inductor, this capacitor. Okay, even
Because
the
these three things
dash
are
selection is also there.
okay.
Yeah, yeah. You
Because
were
this
saying?
passive element selection is the important, I guess.
Yes, yes, yes. It is so much important in this.
Okay, sir.
Okay, so can we move forward?
Yes, yes, sir. Please, sir.
Okay, so so this is the 450 watt panel. Okay, and this is our capacitor. This is our inductor. Okay, and this is our output capacitor. So and we this is our gate bus. We are getting it from the here. Okay, so this here we have generated this one carrier frequency, carrier wave, and we are comparing it with the duty cycle. We have here we have kept the selector switches. So this is the duty which we will be giving. Okay, so that this duty is a constant we are giving, and this duty is being given by this PNO algorithm. Okay, and this here from here we will get the get pulses for this switch, this IGBT. Okay,
Sir, what is the
and
output voltage level of this converter?
output voltage level will be output voltage level will be 2 times the whatever the VPV is.
Okay. Around 70 bar, I guess. 70.
No, three panels we have connected in series here.
Okay. Okay. So that means 3 times. Okay.
Okay, so we will see the simulation. Okay, so
Okay.
first this is a standard test condition, as I said that 1000 watt per meter square power. This irradiation we have kept in 25 degrees Celsius, and at that time this panel should give the 450 watt power, and we will try to get the maximum power at the output of this boost converter. Okay, so here is this MPPT algorithm. So this MPPT algorithm, I think you were asking yesterday that how we can uh, write that MPPT algorithm in the MATLAB. Okay.
No, sir. Actually, my question is that, whether this function block will work in the Weijing block or not. That was
Yeah,
my
yeah,
question,
yeah,
actually.
yeah. Sorry, I misinterpreted it. So this is so this same script we will be using for the Weijing implementation. We'll see in the when we see the experimental video and codes. Okay. Don't worry
Okay.
about that. So this same kind of script we have written in order to in order to obtain the PNO algorithm. Okay.
Okay, sir.
So you see this D duty is a function of I and V. Okay. So we will be just giving the what is the actual sensor, the IPV and VPV. Okay, IPV and VPV are giving, and from that we will be getting the P power, calculating the power. P is equal to V into I, and then the delta V we are getting. Okay, delta V and delta P, and from that we will be checking our condition what we have seen in that algorithm, that if delta p is greater than 0 or delta v is greater than 0, and then in that case we will have to increase the duty cycle, and if it is not the case then we will decrease the duty cycle. Okay, and when the case is changed, the power is get less than 0 and voltage is greater, delta v is greater than 0, then we will also decrease the duty cycle. And
Sir,
vice versa.
I have one question, sir. Here the delta D value is very high, sir.
Yeah, yes, delta
Point.
D is 0.5 here.
It's I think very high, na, sir.
Yeah, if you want to precise operation, you can lower it. Okay, to 0.05 or 0.01. Okay, so in that
Yes,
precision,
sir.
your duty cycle will be varying. But in this case, our duty cycle will be varying in the 50, 50.5, 51, 51.5 in that case. Okay.
Okay.
So is it up to now? Is it clear?
Yes, sir.
Okay. So this duty cycle in this PNO
Sir,
algorithm
what is the what is the utility of this zero order hold, sir? Zero
yeah,
order
the
hold
zero
block.
order holder will change the sampling rate of the whatever the signal coming from here to here. So
Okay.
let's say your signal is running at the lower speed here, and if you want to run it at the higher speed rather than this, then you have to put the zero order hold, and you have to give the sampling rate of the whatever the signal you want is here. Okay, you will see this here. I'll show you.
So such kind of block is not required when we are using the PV array block.
Uh, in the
Directly,
okay. Yeah.
sir, in the MATLAB we are having this dedicated block for the PV array. If we are using that particular block, then this zero order array is not required, right? Or
No,
still
zero.
we,
No. This is not for the power circuit block. Okay, this is for the control circuit only block.
okay.
Yeah. So you see, this is blue color right here. Okay. So the
Yes, sir.
blue color means suggests that this red is your fastest signal. Okay, and
Okay.
blue and then comes green, then this is blue. Okay, and yellow is your hybrid. So you see this yellow we are also converting it to the red, and then it is working in the same speed as the whatever the ts sample time we have set. Okay.
So different block can be run with a different sample time.
Yeah,
Is it
exactly.
possible?
Yeah, that is what we are doing. So we want to
Okay.
lower the processor working. Okay, so we don't want to burden the processor so much that it will do the all the working at the same speed. Okay, so in order to avoid that, we are giving it this sample time.
So, sir, it will not affect the overall computational speed of the control algorithm.
No, it will not affect this control.
Okay. And same thing we can do with STM also.
Yeah, exactly. We can do it. So in
Okay.
order to lower the computational speed and get the best out of the controller, you will have to select the timing very carefully.
Okay. Then what are the parameters by which we can select the
Parameters we
timing
can
for?
select. Yeah. So for the we have said that this your carrier frequency. Okay.
Okay.
Your carrier frequency in 10 kilohertz. Okay.
Okay.
10 kilos. Okay, so this is
Hmm.
100 microsecond. Okay, and
Hmm.
so your maximum controller should be work as a minimum at the 100 microsecond. Okay, if it is
Hmm.
working at 1 millisecond, okay, so then it won't be properly working. Your carrier won't be generating properly. Are you getting?
Yes, sir.
Uh, and if your controller is working at a 10 microsecond, then it will be properly generating the your 10 kilohertz frequency carrier wave.
So, sir, my
Based on the
question is that, sir,
yeah,
my question is that, like we are as I can see in the screen, here we are having 4 zero order hold block. So
yes,
the block which we are using before P and O block and after P and O block having the different color. So both
yes,
are zero. That means both having the different sample time, right?
yes. Same.
So that is actually my question. What at what basis we will select these two different?
Yeah.
sample
Actually,
time.
we want to run this MPPT slow at the slower rate. Okay, we want this MPPT to give the voltage, this duty cycle changing reference at a lower rate. Okay, so you see the sun, the irradiation change occurs not so abruptly occurs. Okay, it is gradually changing, so the clouds coming and the shading happens. Okay, so
Yes, sir.
that's why it is this MPPT we are normally keeping it slow. Okay, so what it will happen is that if we run it at the same time, let's say you are running it as a same time as this rate. So what is this rate time? It is 2 microsecond. Okay, so this block
Mhm.
will giving the duty at every 2 microsecond. It will giving the different duty.
Okay.
Okay, so in order to avoid that, we are keep running it as a lower speed, and then we are again converting that change at the speed of sample maximum speed.
Okay. So that means in the control block where we need the fast calculation, uh, where we can use the more sampling rate, right?
Yes, yes, yes.
Okay.
So is it
Mhm.
clear up to now?
Yes, yes, sir.
Okay.
And sir, in the below the P window block, we are having one particular block which is going to the power, right? So it is for the power calculation, right?
This for this block.
This M, this this MA3, yeah, that block.
It is just average block. It is nothing else. Hello, am I audible? Hello.
It is breaking somewhat, sir. Hello.
Okay. Now is it audible?
Yeah, now it is okay, sir.
So this is just averaging block. Okay. So what we are doing, this Z inverse is a delay block. So what we are doing is Z, we have kept here 1. It is we have kept here 2. So we are taking 10 samples, and that this 10 samples we are averaging and giving it the value of this means we, in order to average the value of this power, whatever power we are getting from the PV, that we are averaging. Okay, is it clear?
Okay. Sir, a very silly question I'm asking. This MA block, can we cannot replace this MA block with RMS block? There is one RMS now.
No, no, you can replace it with RMS. This is just the deal, averaging for the, let's say your this is your 2 microseconds. This is your signal. Okay, so
Okay.
at the uh, the previous sample it will take here the first
Okay,
previous
right, sir.
first
Got it.
second,
Got it, sir.
previous
Got it.
second
Got
second.
it, sir.
Okay,
Got it, sir.
this is how it is averaging. Though.
Okay.
Hope this is clear, and you
Yes,
will
sir.
see the
Please.
waveform. First one right here is the current, VPV, VO, duty, and so you can see this is your current IPV, this is your VPV, this is your boost converter output voltage, and this is your duty. So how you can verify your PNO is properly working? So in order to verify that your PNO is working, is that you get this kind of duty cycle in 3-step duty. You can see this is 64, again 64.5, and again 63, again 63.5, and 64. So it is trying to stay on the this maximum. This is a maximum power point which we have seen here. So it is what is it is doing is it is coming at this point, and it is crossing this point. So what it will say that you have to decrease the duty cycle. So it will again come at this point, and as it was decreasing the duty cycle, it will go again at this point. Okay, so at this point it will again check the power, if it is power is available, and it will say that duty cycle, you have to decrease the duty cycle in order to get the maximum power. So it will again go back to this point. Okay, and when this point, it was increasing the
It is
duty cycle.
oscillating, right?
Yeah, that it is oscillating between this here right now. This three. That's why we will be getting in the 3-step duty. Okay.
Okay, that is why that is why incremental conductance is somewhat better than this one, right?
Yes. So in this, what we are doing is in this perturbing and observing. We are just changing the duty cycle, and we are observing that if the power is available or not. And then we will be changing the duty cycle. Okay, that's why it is called the perturb and observe. Clear? Okay. So this is how the so let's this power we will
Sir,
see here.
I have one question, sir.
Yeah.
Like if we see the second graph, initially power is getting down. What is the reason behind that, sir?
Yes. So that is some issue with the MATLAB itself. Okay, we most of the simulation we get this in initial simulation like this.
Okay.
So we try to avoid this much portion of the simulation portion.
Okay. So same thing, same result we are also getting with the hardware also same.
No. Hardware we are not getting this kind of option. Okay, that's why.
Okay. Okay.
So you see this here, the power is 450 less than the 450 because of some losses in the converter. Okay.
Yes, sir.
So right now your 1000 standard test condition. So now I will change it to the 500 watt per meter square. Okay. So now my power will be half the whatever the previous power 450. Then it will be to around 225. Okay, it should be. See, duty cycle first. We will see that duty cycle is changing in the 3 steps. Okay, you see that it is power is around 190 watt. This is less than the 225 watt. So our power is right now it is half. Okay, we are extracting half power than whatever than the previous power of the full at the standard test condition. Okay, is it clear?
Yes, sir.
Okay.
Sir, what is the range of duty cycle?
So here right now we have kept in the minimum. It will go to the 40. Okay,
Okay.
40 to 90.
Okay.
So
So there is
boost
no
converter
operating,
gives.
sir. Is there any range for the operation?
Yeah, so in order to get maximum efficiency in the boost converter, we want it to run at the 50% duty cycle. Okay, that's why we have kept this minimum range not lesser than the 40% duty cycle.
Okay.
Okay. So we will take a small break here, and after the break, we will see the code for how to generate this, how to develop this MPPT algorithm in the hard Vizum, and also we will see the sensor calibration and PNO algorithm implementation in the hardware. So we will continue at 3:40. Okay.
Okay, sir. Okay.
Okay, sir.
Okay, so till now we have understood the uh, MPPT algorithm. why MPPT is needed, and we have seen how we can develop the PN algorithm, and we have seen the simulation, how we can see the proper outcome of this PNO algorithm, and how we can verify it with the proper waveforms. Okay, so we know that in order to we will be writing code to obtain this in our actual hardware. So we know that in order to sense the voltage and current, we will require some voltage and current sensors. Okay, and that current sensor and voltage sensor will give us the signal in the voltage form of the whatever the current or voltage will represent, and that signal we will be giving to the controller. Okay, so first we will see how we can what are the quantities. In this case we will just need this voltage and current, so we will see the how we can calibrate this voltage sensors and current sensors in order to sense the actual quantity of the voltage, and in order to get the smaller signal of that quantity. So I'll play some video here. So in this video we are going to see how we are going to get our voltage and current sensor. So let us first understand how we are going to calibrate this sensor and what are the hardware configuration of this voltage sensor calibration. Okay, so first you can see this is a circuit diagram for calibrating our voltage and current sensor. So you can see from the on the left hand side that this is a for single phase variac, and this single phase variac is connected to the bridge rectifier. So the rectifier will convert the AC into the DC. So that DC we are using, we are filtering through this capacitor, and we have connected our V3 sensor card, which is made by us, and this is our load connected. So as I explained in this circuit that this is a single phase variac. So in the actual this is our single phase variac, and the output of this single phase variac we have connected to this bridge rectifier. This is our bridge rectifier, and the bridge rectifier outputs this DC. So this bridge rectifier and the DC of the bridge rectifier, the capacitor. You can see this. This is the capacitor connected on the rectifier output, and that rectifier output is directly connected to this voltage sensor. This is our V3 sensor card. And the voltage sensor we are giving this here the input positive and negative, and from this here we are connecting our load. So this dark blue, you can see this is our voltage sensor, Hall effect voltage sensor card, voltage sensor, and this is this sky blue color is a Hall effect voltage should be connected in parallel. So this current sensor is connected in series, and this voltage sensor is connected in the parallel. Hope you understand this circuit, and we will see the sensing calibration of the voltage and current in next video. So shall we see the second video?
Yes, sir.
So we will see how we can calibrate the voltage sensor, DC voltage sensor. Okay. As we have seen the setup of this voltage sensor calibration, so first we are going to calibrate the voltage sensor. So or we are going to set the actual voltage of 200 volt, and our sensor should give 3 volt at the 200 volt DC. Okay, so So I'll first we are going to give first the supply, turn on the supply first. So I'm turning on this single phase variac, and now I'm going to give, this is our DC link output voltage. So I'll set it to the 200 volt DC first. So as you can see, I'm gradually increasing the DC link voltage by varying the variac. What else? Actually, we were setting it for the 100 volt first, then we will set the for the 200 volt. Okay. So this is our sensor output from where we are getting the scaled down voltage. So this V out, I out, and ground. So from the V out, we will be getting our voltage of 3 volt. Okay. So we have connected this DSO probe on this red voltage out, and the black one is a ground pin. So we will observe we will calibrate this 100 volt. Accordingly, we want to calibrate it on the 200 to 3 volt. So at the 100 volt, we should be it should be of 1.5 volt. As you can see, the calibration we have write it down. So we are calibrating at the 1.5 volt. So on the DSO screen, we will I'll vary this port on the our V3 sensor card, and we'll try to set 1.5 volt. As you can see, the voltage is coming down. So this mean value, the maximum value, it is a DC, so it won't be affecting. So I'll set it on the 1.5 volt. It is lower than 1.5, so I'll try to find calibrate it. So it is 1.5 volt. So now we will gradually increase the voltage to 150 volt, and at the 150 volt it should be giving us the 2.25 volt. So that we will verify by giving first that 150 volt DC link, and on the DSO screen it 2.25 volt. So the DC I have set it to 150 volt, and we will observe on the DSO that DC link is the voltage is scaled down at 2.2 to 27 volt, which is nearly 2.25 volt, and to give it a seal of proper calibration, we will again give it our voltage of 200 volt, and we will see the 3 volt. It should be giving us a 3 volt output. So I am increasing the voltage to 200 volt. As you may be able to observe on the DSO that the line, the DC voltage is getting increased. The value of DC voltage is getting increased. So now I have set this voltage to 200 volt, and you may be able to observe that the 3 volt is giving us the output. So, and you can see the voltage DC is set to 200 volt. So now this is how we are going to calibrate our voltage sensor. I hope you understood it. Thank you. The calibration part of the voltage, is it clear to everyone?
Sir, for every operation it is needed, sir.
Can you specify what they mean by that every operation?
Suppose, sir, Whenever we use the sensor card, then it is necessary to calibrate that one, or it
If
will
you are
depend upon the microcontroller in which we are working.
no, you will have to scale down. But if you are, you know that your calibration is 200 by 3, and you know your application. If you require, if your voltage will be not, they will be not more than the 100 volt, then you will have to again calibrate it for the in order to get the precise operation. Okay, precisely.
And how we can measure the current, sir?
Yeah, yeah, that I will also show. Okay, okay. So let me play that video. Then we'll see the code. Okay, is it okay that if we see the current calibration first and then we'll see the old code, or should I explain how we the voltage we have sensed and how we can calibrate it in the
As your wish, sir.
Hello, Mr. Junaid. Hello. So can you hear me? Anyone, please?
Yes, sir, you are audible, but Junaid sir is not audible, sir.
Mr. Junaid is not audible. Okay, okay. I'm calling him. Okay, 1 minute.
This PCB.
hello. Am I audible to everyone? Is the screen visible?
So your screen is
Yes,
now
sir. Now.
visible. Earlier it was not visible.
Okay, okay.
Just now it
Now
is
is
visible.
now it, okay, okay.
Now we are connecting this on this IOUT. You may be able to see on your screen that this IOUT where we have connected this DSO probe. IOUT and ground will be the same for both. So now I'm going to give it 2.5 volt, 2.5 ampere current. So now I'm gradually increasing the current, and you may be able to see that is 2.5 now. Okay, so I'll set it on 2.5. So it is 2.5 set. And now I'll vary this for the voltage. You can gain port, and for the current, this is a I current gain port. So now I will vary this port, and we will observe on the DSO that it should be of 1 volt. So you can see that this is 390 millivolt. So now I will set it to 1 volt. So you can see this. It is on the Z direction. So at the 2.5, it should be of zero point 0.5 volt. For a zero point 0.5 volt is 500 millivolts. So now I said at the 500 millivolt. So now it is coming to the 500 volt, 500 millivolts. Sorry. So it is set on the 500 millivolt. So at the 2.5 ampere current, this sensor is giving us the output of zero point 0.5 volt. So now I'll increase the current to 5 ampere, and we'll observe it should be giving us the 1 volt. You can see the calibration which I have written. At the 5 ampere, it should give us the 1 volt output. So now I'll increase this 2.5 ampere to 5 ampere. We'll quickly observe it on the DSO that it should be giving us the 1 volt. So you are able to see that this is giving us the 1 volt. So now our sensor is calibrated at 15 ampere. It would be giving us the 3 volt DC output from the sensor. Hope you understood this sensor calibration of voltage and current. Thank you.
So you guys, is it clear how we can calibrate the
Yes,
current?
sir. That means in both the cases we are actually measuring the voltage, right?
Yeah, we will be measuring the voltage.
Okay.
So as you said that we will be measuring the voltage, okay, and we will be giving it to the our ADC of the controller, okay. So ADC, for that we have this, given this ADC. ADC, we have selected this A1 channel. On A1 channel, we are sensing this current. Okay, so current, whatever the current signal we were getting from that voltage and current sensor, we will be connecting here on the first channel ADC. Okay, and this is this what block, which is this block, Yugal sir?
Averaging blocks are like we are using.
Yeah, exactly. Averaging. We are taking here so many average of 20, 20. Okay.
Sir, what is the utility of these blocks, sir? I'm not able to understand.
This average.
Yes, sir.
Okay. So the average. So let's see. Let's say what will be the this signal will be carrying. This is your ADC, right?
Yes, sir.
So yesterday we
So
have seen it is 12-bit ADC. Okay. So it will give us a count
sir, okay,
count in the range of 0 to 4095. Okay, total of
okay, okay,
4096 count. Okay, so your
okay,
count, you will be getting count respective to your voltage, whatever voltage you are providing. Okay,
okay.
you have already seen that video where Rajan sir was showing that he was varying with the ADC port, and we were observing the count on the LCD screen as well as the voltage
Okay, okay, okay. Right,
on
sir.
the
Right, sir.
right.
Yes, sir. Yes, sir.
So your count will be vary accordingly. You will have to convert that count into the according voltage, and that voltage here you see is 4095. Okay, 4095 to 3.3. Okay, that you have converted into voltage, and then that voltage you have changed into whatever the calibration you have kept, 15 by 3. Okay, so you whenever you get 3 voltage, it will say that 15 ampere is there. Okay, this is
And
the
sir, suppose if we connect this ADC block directly to the gain, then what will happen, sir?
yeah. It can also give you that. I'm coming to this point too. Okay,
Okay,
just I'm saying how we can use this gains. How that count we have converted first into the voltage, and that voltage we have converted into the whatever the calibration we have set into the current. Okay. So the averaging part is there. What your count may be varying. Okay. So at the first one sample, your count is let's say 3,000, and and after that sample, your count is coming something 200 and 2,090 900. Okay. So so it takes that 20 samples of that and takes the average of that 20 samples and gives the output of the 20 samples. Okay, that's so that your oscillating value you won't be getting.
Okay. Okay, right,
Okay,
sir.
that's why this averaging is used. Okay, so this is how you calibrate this current. Okay, 15 by 3, and this current we have given this is PNO algorithm. Okay, I okay, and again for the voltage we have this another channel PA0 AA0. So that channel we will be giving getting our giving our voltage signal, and again we are averaging that, and that averaging again converting that count, whatever count coming here, into the voltage form, and this voltage is then converted into the actual voltage range give with the calibration factor, the 200 by 3, and that it the whenever the sensor is giving a 3 volt, then this controller will understand that it is right now the 200 volt. Okay, is it clear?
Sir, rate limiter will limit the upper sample and lower sample, right? Sir, this rate transition will limit the
No. It is
rate.
not rate limit. It is rate transition. It is just the whatever. It is also kind of similar to the zero order hold.
Okay.
Match the timing between these two. Okay.
Okay. Okay.
It is not having so much that much functionality. Okay.
Okay.
So this is understood. Okay. So then after this current and voltage, we are giving it to the again our uh, duty. Okay. Duty we are giving. Okay, so duty we will be getting out from this piano algorithm, and we have the duty this block is giving us in the range of 0, 0 to 1. Okay, that's why we are multiplying it to the 100. Okay, and then we have given some saturation. Okay, the saturation it will be whenever this duty cycle is exceeds the 85, it will this upper limit upper saturation will be 85. So our gate pulses won't be getting more than the 85% duty cycle, and it on lower it won't be lesser than the 45% duty cycle. Okay, is it clear? So this
Yes. Yes,
duty
sir.
So this duty cycle we are giving it to the our advanced PWM. Okay,
Okay. Okay.
advanced PWM. In advanced PWM we have set this. You know that how we can set this.
Yes, sir.
So what is the we have said this timer 8 we have taken this advanced PWM block, and PWM period is here 25 microsecond PWM period. So what is the frequency here? Switching frequency.
Well, switching frequencies 20, the time period is 25 microsecond. That means 1 upon 25. Mm, switching frequency is 1.25. 40, 40 kilohertz.
Yes, exactly 40 kilohertz. Okay. Timer counter mode up. What is suggest? And timer counter mode up.
Sorry, I think in advanced PWM we are having two pulses. Then, so I think only one pulse is needed. I think, no, in this case.
Yeah, exactly. Only one pulse is needed. But counter mode up, what it is mean is our triangle will be like right aligned triangle like this.
Yes, sir.
Okay, not like this left aligned triangle, and also not like the center line like this. Is it clear?
Okay. Yes, sir.
So that
So that
that will
it
be the
so
yeah
that
yeah.
it, whatever input it is getting from the IN3 port, it will compare with this left aligned
Not IN3 code, not IN3. Oh, yeah, IN3. It is all not nothing other than the duty cycle.
Okay.
See, you see that here the DPV, where it is coming from. DPV it is coming from here.
Yes, sir.
Okay, so it is nothing else than the duty cycle. Okay, so
Okay.
this also this subsystem. You know what is happening here? What the duty cycle we are giving? The duty cycle it is getting inside, and this advanced PWM we are giving the duty cycle. Okay, and we have
Yes, sir.
kept this enabled. So what will happen is that this subsystem will be enabled, when we are pressing our PT7 button. Okay, we will see in the that experiment. Okay.
To initiate the operation, we need to press the button, right?
Yes, exactly. So whenever we press the button, this and operation will take place, and then whenever the one will come here, this subsystem will be enabled, and then when this subsystem will be enabled, the what we are kept in here is the timer 8. So that the timer will turn on at that time.
Okay.
Okay. Until unless it will be off, the timer won't be generating any carrier waves and comparing it with the whatever the duty cycle we are giving. Okay, is it clear?
Yes, sir.
Okay.
And sir, what is the utility of this? There is one more subsystem. Sorry, there is one function in the downside, sir. Left side, sir.
Okay, yes,
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 sir. No, sir.
yeah,
In the down one, sir. Yeah. Start and
this
it is for the to initiate the program, sir.
is you are talking about this right now.
Yes, sir. Yes, sir.
Yeah, yeah. So this is just DC link lock. Okay. So
Okay.
we are preventing for prevention of the boost converter. Let's say the boost converter. Uh, so what happens that so many of the students and even some faculties when they are running the boost converter, they do not connect the output load at the output side. Okay, so
Okay.
in the open circuit, when you have not connected the load, what happens is your energy be getting stored in the push converter, that capacitor, and it will the voltage will be increasing and increasing.
Okay.
So in order to avoid that, we have kept here some lock. You see this 350. So if your voltage output
So
voltage.
so this particular function will take care of the maximum output of maximum voltage of the DC link, right? Suppose this particular limit will cross, then it will automatically off.
Yes. It will automatically state. It will change the state to 0. Okay, the state it will become
Okay.
0. And what we are getting when we are using this state, this is here. Okay, even if our PD7 button is giving us 1, and this state becomes 0. So ultimate our this output of this will become 0, and the timer will be turned off.
Okay.
Okay, is it clear?
So I think for that purpose we need one more voltage sensor, to sense
Yes,
the.
exactly. So you see this here we have again used one ADC channel. Okay.
Okay.
So this ADC channel we have used. Okay. So and it is calibrated again and converted again into count into the voltage, then count into the voltage, and again we are using this calibration. But here our this will be changed, because this was our input voltage of the boost converter, and this will be our output voltage of the boost converter.
Okay.
It will be calibrated at the different rating than the whatever the input was calibrated.
Sir, what is the maximum voltage that we can measure through the sensor that you have shown?
uh, you can measure up to 1200 voltage.
Okay.
Okay.
Both AC and DC?
Yeah.
Okay.
So so this is clear, right?
Yes, sir.
and it says there's some functionality. There's the input button and all of that is given here. On the DAC we are also observing duty cycle and also observing the power also. Okay. Yeah. So shall we see the experiment of this?
Yes, sir.
Okay.
So welcome guys. This is our setup of MPPT.
At any point if you're not able to see or listen or see the video, you point out to me. Okay.
Yes, sir.
Boost converter. So first let us understand the setup itself. So from the input side, we have terminated, as we have seen in the video, that we have terminated 6 panels, and we have seen on the 6 panels are on our facility of 150 volt each. So 150 watt each. So right now we are using these 3 panels, which we have connected in series. You can see that this three first, second, and third channel we are using in series. So you can see the positive terminal of this first panel is connected through this emitter, and it is going. So this input terminal of the boost converter. So this is our input current, and this is our sensor card, V3 sensor card, as which we have in the DC sensor calibration, and it is connected in series for the current and in the parallel for the voltage. So the same voltage which we are sensing here is connected here with, through the voltmeter, multimeter, and moving on to the boost converter. You can see this is the inductor, input inductor, and then this is our driver card for driving the switches, and this inductor is of 5 millihenry and 10 ampere rating. And on the driver card of the this is our driver card for driving our switch of the boost converter. You can able to see this is our switch, and this is the diode. For that we are giving a in the boost converter operation, we want to use only, we want to give only one gate pulse. So that's why this switch will only get the gate pulse, and this switch won't be getting. This is a diode. Okay. So moving on to the output side. So output side, the capacitor is connected in parallel, which is his, and at the output we have connected 400 watt load, which is this 2 bulb of 200 watt each. So coming back to the controller. So as first, let us understand the sensing, which input sensor. Input sensor. So this input sensor which we have connected at the panel terminals. So with that we are terminating from here to the ADC channel of our
Junaid sir, it is not coming.
Uh, Hello, excuse me. Hello. Mr. Junaid will join very soon due to the some technical issues at their end. So he will join very soon. Please patient.
Hello. Sir, am I audible? Everyone, am I audible?
Yes, sir. Yes, sir. Sir, you
Okay.
can start.
Thank you, sir. So there was a power cut at our facility, so that's why internet was disconnected. I will share again from where it was left. We have just 5 to 10 minutes are just remaining in completing today's session. Hello.
Yes, sir, it's
Yes, yes.
visible.
Visible. Visible. Visible. Screen is visible.
Hello. Okay, thank you.
Oh, it is. Calculate through the internal process which we have seen in the code. So this is the power. Timer 8 pin, which is PC6 pin we are using. So this PC6 pin gate bus which is given through this port. So this gate bus is getting to this switch. So this key we are using to turn on our MPPT, which is of piano. As you can see, we have connected this probe at the gate bus of the switch, and we can observe there is no pulse right now on the DSO screen. So now after pressing the switch, this PD1 switch, we will observe the MPPT is taking action, and the input voltage will be reducing to its current irradiation condition. So now we will see the before MPPT condition. So this multimeter, as we have seen, that it is measuring the input voltage, which is 112 volt, and this is the measuring input current, which is 0.334 ampere. And you can see this is connected at the output of the boost converter, and it is the same as the input current, and this is the output voltage, which is also 111 volt. So now you can see the output and input and output voltage both are same, and you can also see the brightness of is less. So when I'll switch on the MPPT, so the brightness of the bulb will increase. So the and accordingly the input voltage will be coming to its maximum voltage point, and it will give us the maximum power. So now I'll turn on the MPPT, and you will be able to observe the brightness of the bulb will increase. So now you can see the brightness of the bulb is increased, and you can see the input voltage is reduced to the 100 volt, which was in the previous case was 111 volt, and you can also observe the output voltage, which is 180 volt, and the applied duty cycle, which is 45% duty cycle. Okay, 47. So the MPPT is taking action to reach its maximum power point. So now you can see the voltage, input voltage is 100 volt, 102 volt, okay, and input current is of 0.9 ampere. So this is the after MPPT. So this is the voltage and current of the current irradiation. So you can see the voltage. So you can see the current and the voltage, for the current ambience current in the irradiance. So you can, this is the our output current, and you can see the brightness of the bulb. So, and this is our output voltage. So let us first see. So you can observe the output voltage is 440 volt, and you can see the input voltage and input current, which is 94 volt, 100 volt, and 3 ampere, which is around 300 watt, so 350 watts. So you can observe. Okay.
Junior sir, video is stuck.
Hello, any issue? Junaid sir? नहीं, नहीं, नहीं. Hello, Junaid sir? Yugal sir? Hello, Yugal. Mr. Yugal.
Yes sir, video is stuck sir, actually video
No, I think
काम नहीं कर रहा
there
है.
is a problem from Anatech side.
Yes sir.
I have already shared the feedback link. Please put your attendance.
Yes sir. Yes sir.
I think just 5 to 10 minutes are remaining. Let's wait. We can wait.
I think last 5 to 10 seconds, I think maybe it was not played.
Okay, let me again play it, and please tell me from where it was.
One pulse per 5
Was this
seconds.
covered?
No sir, no sir, no sir. Before that,
This was
no sir, no, 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 no sir. Yeah sir, from that point sir.
okay.
It is,
Yeah.
yeah.
So now we'll verify our gate pulse of the boost converter. So you can see we have connected this DSO probe here, and this is the 40 kilohertz pulse. So you can see this is a 40 kilohertz pulse. So 40 kilohertz means 25 microseconds. So you can see this is the type of division is in 25 microseconds. You can see the one pulse is getting completed in 25 microseconds. now I changing the time per division, so you can see that it is now 5 microsecond. So you may be able to observe that it is completing in 5 seconds. 1, 2, 3, 4, and 5. So the duty cycle, you can observe that duty cycle is 75%, and you can also observe it on the DSO LCD scale. So this is 73% duty cycle. So you can how we can say that our MPPT is properly working. So you can see that 3-step duty. It is the MPPT is giving. It is changing in the 3-step. So that is the verification of the MPPT working properly, which we have already seen in the sim.
Is it? It is. Audible? Hello.
Yes, sir.
Yes, yes.
Hello. Am I connected?
Mm, yes, yes. Yes, Mr. Junaid.
Okay. So, so, so today we can conclude. So it was all for today's session.
Okay. So thank you very much, Mr. Junaid and team of National Infotech Surat. Any question from audience side? So we are extremely sorry. Hello. We are extremely sorry due to some interruption occurs due to power cut at National Infotech side.
So we deeply apologize for the interruption that our power cut was at our facility, and also the internet issues were there. So that's why the few disconnection was there.
So, so I request audience, please, if you have any query, please ask. Okay, I think no query. So once again, thank you, National Infotech Surat, behalf of SSBT College of Engineering and Technology and Department of Electronics and Telecommunication and Electrical. I would like to thanks the whole team of National Infotech Surat. You have explained very nicely different modules as well as some algorithm as well as some simulation modules of PV cells, solar PV system. Okay, thank you very much. Uh, some announcement. Tomorrow there is a lecture on digitally controlled converter system for photovoltaic applications by Dr. P.V. Thakre. So please join tomorrow morning session at 10:45. Please join in advance 15 minutes. So for the smooth conduction of the program. Okay. So he will deliver on the lecture on photovoltaic applications. Okay. Thank you very much once again. National Infotech Surat team, National Infotech Surat, and Mr. Junaid.
Thank you, sir. Thank you.
Thank you, sir.
Thank you very
Thank
much.
you.
Yeah. Okay. We'll see you guys tomorrow.
1 minute, just link is given. Link of day one is also given on WhatsApp as well as on chat box. Link of day two is also given on the both side. Please, please note down.